So I'm starting a little early just to keep us on schedule and not steal too much time for the speakers. Still okay to mingle around. We have live streams going out to YouTube and Periscope, hopefully. So without further ado, I'm your host with too much beer today, but I'll try not to look like an axe murderer unless something is really wrong. You have the tags. Tweet if you see something cool or ask me questions. We love you, all speakers. Once again, we managed to come up with a really wonderful lineup. We're starting out with Mr. Purdy, who's also talking about the Ecstasy language at the conference. And Charlie Gracie later in the day will also talk at the conference. So they have some other opportunities to see our speakers there as well. So that's it. See, I did it. It's in the middle of my slide here. But the camera will get you, even if you're to the right. That puts us at 9 o'clock. And I'll just give the stage to Cameron Purdy. It's going to be very interesting to see the inner workings of the XVM. So thank you and welcome. And it's great that you're here with 1 hour of sleep as the first speaker.
All right. So my name is Cameron Purdy, and I am talking about the XVM. So how many people actually have any idea what the XVM is? Excellent, like 5. That's 4 more than I thought. This is this is an actual like greenfields project. We started a few years back with a business plan that was completely impossible. And then as we were designing what we wanted to build, we realized that none of the existing languages, except maybe JavaScript, were suitable for what we wanted to do. And for some strange reason, we didn't choose to use JavaScript. In the course of that, we went through several iterations of design. And so what I'm going to be talking about today is as much design as it is implementation. So our current XVM implementation is actually a proof of concept. And that's because we're still screwing down some of the last details of design. And it's a lot easier to change details on a proof of concept than it is once you, start, building a compiler backend. So away we go. The XVM is a portable runtime. It's designed for everything from the device through the through the edge, which would be very interesting in 5G, where parts of the application may be running, just meters away on a local pole, all the way back to back end, which more and more is what we call the cloud. This is me. Previous to this startup, I was at Oracle, and previous to that at Tangosol, which was acquired by Oracle. So my background is some mix of coding and other stuff. So this is the kind of warning slide. So like I said, right now, the implementation of the XVM is just a proof of concept. Please don't make any judgments of the design based on the proof of concept. But the specs, we've almost got everything nailed down. So I made up a version number that sounds, opportunistically close to 1.0. And I think hopefully you'll see some of that today. So our design goals were driven by, like I mentioned earlier, by a business plan that we put together, which I won't actually go off in that direction because it's unrelated to the technology itself, other than the fact that it needed it. But basically, we were looking at how do we run many thousands of applications on a single server, and that was something that was relatively difficult to do with other infrastructure. And so what we're looking for was something from a managed VM point of view, something that could do ahead of time compilation without obviating the capability to do adaptive compilation. Adaptive compilation, of course, is made famous by the hotspot JVM, which basically collects some amount of profiling information at runtime and then feeds that back into a compiler, which then produces very, very optimized code somehow. When I say very, very optimized code, that's from it's a very complex system, so it's not the same type of optimized code that you'd expect to be writing in assembler. But what makes it particularly interesting is some of the optimizations it can do are theoretically impossible, unless you can, both build bridges and burn bridges at runtime. And so Hotspot's interesting, for example, because it can potentially inline things that are virtual calls. And then, so there are a number of things that we saw, I started using Hotspot back in '97. And, a bunch of ideas that are really inspirational in terms of just thinking about a running system, not as a byproduct of some ahead of time compilation that happened, a year ago and created an image, and not necessarily just as a just in time compilation, where as you start up, you do the work of turning some portable binary into an executable code, but actually this idea that at runtime you have the ability to make, anyone watch the Super Bowl in the middle of the night? Like a Hail Mary. I didn't watch it either. I was writing these slides. Like a Hail Mary pass is what we would call it. Like go way down the field with the ball. And in a way, some of those optimizations are the things that are opened up by the ability to create a predicate that says this is what I assume to be true, and as a side effect of that assumption, I'm going to take this code that shouldn't be inlineable and I'm going to inline it. And now, anytime that this predicate turns out not to be true, I know to go back and either undo or put that's what I'm looking for. A conditional in front of the need more sleep. A conditional in front of that optimization. So, as I said, adaptive statistics, it's designed for an adaptive statistics-driven model, but not just for code optimization, also for threading. And this one is incredibly important. And these are just, if you will, two examples. This isn't the limit to what we're thinking about, but there's nothing more dangerous than a developer writing multi-threaded code. There are roughly 4 people in the world who can do it right. Turns out that even the people who can do it right can't do it right. So, I don't know how many times Doug Lee has said, "Oh yeah, you're right, that doesn't work." Guy's brilliant. That's all he does is, multi-threaded code. If you're going to get rid of threads by hand, there has to be something to replace it with. And one of the other things, like I didn't put it in the slide, but I'm going to back up and kind of explain it. In the ancient history back right after we invented the wheel about 30 years ago, the software optimizations, you kind of had these different tiers, right? So you had like the disk, which was like glacial, and then you had like RAM, which was pretty fast, and then you had like, if it's inside the CPU, it's really fast. And those kind of in the 90s, it kind of played out pretty well. If you're optimizing, you were thinking, okay, I'm going to try to keep it on the CPU, and then RAM's fine and disk is horrible. Now, if you look at a running application and you profile it, touching the memory is glacial, right? Doing a load out of main memory, it's like you're stopping you get a couple instructions done, then you hit a cache line that's missing. You go out to load it, and it freezes because you've got CPUs that are pumping billions of cycles a second, and each of those cycles is capable of retiring several instructions. So if you can't keep the caches correct, if you will, not correct from if you can't keep the information you need in the cache, it has a dramatic impact on throughput. So obviously, a couple platforms that we're targeting, and one of the reasons that we think we can pull this off is because of the LLVM project, which has been successfully used by quite a few different back-end projects at this point. The other design thing that we were really interested in was being able to basically consume an entire unit of hardware. So we designed this for, at the time, server CPU was maybe 20 cores or something. We designed this for machines with 1,000 plus cores, and that's because we saw the trend. We knew it would go there, and massive amounts of memory. The number we used at the time was 32 terabytes. Now, if you're managing 32 terabytes in a process, as you can imagine, there's some potential problems with that. But our plan is in a single process space to be able to manage, to basically consume 100% of 1,000 cores and tens of terabytes of RAM. So the design was for that purpose. And then security. If you're going to run more than one application on a machine, it has to be impossible for one of those applications to see another application. So this was part of the design for the system. So how did we achieve this? Well, the first thing is the runtime model is actually a hierarchical container model. What that means is that the XVM has a pretend initial container. We'll call it container -1. So if you think of a ring model in a CPU, you could think of this as ring 0 or even ring -1 if it's imaginary. And that is the container within which we materialize the type system for the intrinsic type system of the XVM itself. When I say intrinsic, I don't mean primitive. There is no actual primitive type system in the XVM. It's a purely object type system. But without having a primitive type system to rest upon, we have to actually construct our type system is what we call a turtles type system, meaning all the types are composed of other types. So, for example, an integer is composed of, among other things, an array of bits. And a bit is an enum, I think. Actually, no, a bit is not an enum. We have an array of bits. A bit is holds on an integer literal, which is either 0 or 1. Integer literal holds on a string, and a string holds on characters, each of which has code points, and code points are ints. So ints are composed of ints. So the size of an int is, Charlie? No, infinite. The size of a single int is infinite because it's composed of itself. So obviously that type system, can't exist for real. So we mount that turtles type system in the first container, and then the next container you could think of how many people program in Java. So when you write a main in Java, that's the next container that gets created, and that container takes whatever modules you've specified to run, and it inherits the modules from the container above it. So it inherits the turtles type system. And then, for example, for a hosting platform built on this, you would then construct a series of containers under that kernel container for actually hosting applications. So each container has its own type system, and it can inherit all or some of the type system above it. All containers inherit the base type system itself. And when we do that, we now know within that container the entire domain of types that container is responsible for. And so this is what's called transitive closure. So transitive closure basically means you start coloring and you don't stop coloring until you've colored everything. And that whatever you've colored, that's transitively closed. So in other words, it's like what GC does on the mark portion of GC, except we do that with types. And the reason for this is because most cool optimizations, for example, cannot be done unless you know all the types. And so we designed this from the get-go that all the types would be knowable within a type system. And then anytime you need a new type system, you just create a new container. Then we use what we call a service. Now, service is the most overused word in the industry. So even if this is a small service, it's not the microservice that you know. And if it's a big service, it's probably not the service you know. We use the term service as it has two meanings. The first meaning is that it's the boundary for mutable state. So no mutable state can leave that boundary. No mutable state can enter that boundary. That means you cannot see mutable state from another service as mutable state. Now, you can ask all sorts of questions. It can answer those questions. But you can't, I'm sorry, I have to clean up my language. I was about to say something bad. You can't mess with the state in another service. So every service has its own domain of memory. Now, that's pretty cool. We'll get to the memory model, so I'm not going to steal all my thunder on that. But the second part of what a service is it's an asynchronous boundary. That means if two services are talking together, they could both be running concurrently, and the means of communication could be as some asynchronous queuing mechanism, like all the small talk, not small talk, Erlang processes. So why is this important? Well, first of all, it lets us get rid of the thread concept. There are no threads. Well, obviously there are threads somewhere hiding underneath, but they're not raised as language objects. So that means you don't have to worry about how many cores are on the machine, because it's going to manage the mapping, the end-to-end mapping of things that need to be run against the available hardware resources. We also have nothing like thread synchronization. We have nothing like wait, notify, etc. So those are all just gone. And then by default, when a service talks to another service, it just looks like a method call. So this is what's called async await. You call another service, you get an answer back. You have no idea if it happens synchronously or asynchronously. And the side effect of not knowing that is you didn't have to write any code to not know that. Bonus, right? On the other hand, if you really want to know, you can use an explicit future, which is also called a promise in some language. And this works for both synchronous and asynchronous. So even if you don't know that you're talking to a service, you can still use a future to call whatever that function or method is. And then the result will be treated the same from the caller's point of view, but the mechanism under the hood is different. So anytime a call comes into a service, that's a fiber. Conceptually. Doesn't mean that we create a fiber object every time a call comes in, but conceptually, every entry into a service is a fiber. So even though a service is completely single-threaded, did I put that up there? I think it's on one of these slides. So a service is completely single-threaded. That is, it never has two concurrent threads running inside a single service. It can have many, many fibers. So because of asynchronous I/O, you can have calls coming into a service, it turns around, does some I/O, and then it's waiting on a future or an async await. Another call comes into the service, and if you've allowed that to happen, so a service can prevent that from happening. You can say, no, I need to finish my work before anyone else comes in. But generally speaking, any service can allow any number of calls to come in. So a service becomes, if you will, a unit of concurrency, the unit of concurrency. Again, just a kind of a design point, our assumption is 10,000 plus containers, over 1 million services in a single process. So when we say service, think, anyone use Erlang ever? Okay, excellent. That's more than I expected. About half a dozen people. In Erlang, how many processes can you have? Yeah, as many as you need, right? Like just spin them up. The difference between what we've done here, and I've never used Erlang, so I'm speaking as a person who knows how to read things online. The difference between what we did and what I understand Erlang did is that everything in Erlang is a process, is an asynchronous object. And here, a developer would specifically say, no, this class is a service. All right, memory model. So we alluded to some of this on earlier slides, but a service is the boundary for mutable state. So what's really cool, just to go, never mind. Yeah, this slide, back one slide. Like, there's a lot of like things that are said here, but it doesn't really spell out like why all these decisions were made. And one of the benefits of this is the memory model is not a side effect. It's the reason for this. And what I mean by that, one of the things that slows down code the most is having to deal with, say, a memory model, where it has to make sure that the reads it's doing are correct and the writes it's doing aren't being lost. And if you only have one thread at a time working with mutable state, your memory model basically becomes one paragraph instead of a book. And that's a lot easier to get right. There's no way to explain to a typical developer what a C++ memory model looks like. In fact, they're still trying to figure it out themselves on the standards group. So it's and Java's memory model is mostly there. In fact, C++ mostly stole it. But again, it's very complicated, and most typical developers do not understand it. But the cool thing about having each service responsible for its own mutable state is that GC is never bigger than a service. So your stop the world pause is now stop a service pause. And if you have 1 million services, that's probably a smaller pause. Now, a service could have terabytes of memory of its own, so it could still be a significant thing. But each service you can almost think of conceptually as a logically separate CPU. It's its own von Neumann architecture. So each container is itself a service. So this is, like I said earlier, the type system is called a Turtles type system. Does anyone know the reference Turtles type system? Turtles all the way down. That's right. So for those of you that don't know the story, this physicist was giving a talk, and a lady came up afterwards, and she's like, it's all very interesting and everything, but we know that the Earth is actually carried on the back of a turtle. And he looked at her and said, oh, I'm thinking he was smart. He said, and what does this turtle stand on? And she says, well, another turtle. He said, and what does that turtle stand on? And she goes, oh, you think you're smart, but we all know it's turtles all the way down. And so that's the type system. And in fact, the way the type system works is when you pick up a turtle, there's always a turtle underneath it. So you can go down as far as you want, asking what's under this turtle, what's under this turtle. And there's always another turtle underneath it. But the turtle you don't pick up doesn't have anything under it. So each service is within the context of a container. So we have a hierarchical container model where the container itself is a service, but also contains any number of services. So think of a container as an application. When I load an application, I'm going to load it into a container. The container itself has its own service that represents the container. And then anytime I create an instance of a class that is a service class, I get another service, which again is like its own von Neumann architecture machine. Now, in addition to each service having its own memory space, the container can also have a dedicated space for immutable data. And that's because services talk to each other using immutable data. And since a service can't reach into another service to grab data out of it, when services communicate with mutable data by reference, and again, there's no, from a machine point of view, there's no visibility of reference versus value semantics, which means that when one service is calling another, it could be passing by value, like the number 4, or it could be passing a reference to an object that is the number 4. So anytime it's passing by reference, the thing being passed by reference has to be one of two things. It has to either be a proxy, which is someone else's view of your service, or it has to be immutable. So immutable data is copied as necessary to this shared slab that's managed at a container level. So, and as you talk, if a container has to talk to another container, then it's escalated up the tree to the place where those two containers meet. Now, why is it cool to have a slab just for immutable data? Well, immutable data is really easy to GC because it's stop the nothing GC. And the reason is because immutable data is, you can have two copies of it and they're both the same copy. So when you garbage collect immutable data, all you do is you there's so many good terms, I can't remember them all. But basically, any piece of data you still use, you copy to the end. And you copy to the end. And now I'm messing up the picture. And you copy to the end. High picture. And then someone else comes along and they do the same thing. So if there are, say, 10 different services that could be using this, you start with a number 10, and it goes down to 9, it goes down to 8, it goes down to 7, it goes down to 6, it goes down to 5. And when it gets to 0, whoever gets it down to 0 just throws the old slab away entirely. So in the meantime, though, until that slab is thrown away, some references are to the old slab, some references are to the new slab, and nobody cares because it's immutable data. So again, this is, as you can imagine, if you're trying to be able to consume 30 terabytes of RAM without stopping ever, having a mutable state that can be concurrently collected is incredibly important. And being able to create an immutable class just by changing one keyword is a pretty handy capability. So we'll talk language on Wednesday. Invocations between services, they behave as if they're asynchronous message queues. Now, what's cool about this, and in fact, we've already started prototype some of this in the proof of concept, is that in that hotspot sense, you can use any number of different ways of communicating between two services. So we use metaphors such as hoteling, I think is the term used for it, where basically each room can only have one thread in it at a time, but the rooms are adjoining. So if you go into another room and the door is closed, so there's no sign on the door, no one's in there. So you just open the door and go in, and now you hold two rooms, right? So now the cost is for someone to get you out of the old room because you're now in a different room, right? So in other words, a single thread can jump from service to service to service. So it doesn't have to be implemented as a queued asynchronous model. It could be implemented synchronously for purposes of performance. But once you realize that, hey, that room, we keep trying to get multiple people into that room, so we're going to change the proxy, which is just a function pointer. We're going to change the proxy for going into that room to use, for example, a queue. So on one extreme, you have a queue with possibly even a dedicated hardware thread if it's busy enough. And on the other extreme, you have synchronous code, and it's figured out by the runtime. Good to see you nodding. It's hard to explain some of these things. I've been trying to get the language down for quite a while. So like I said, or not. Maybe it's not an async message queue. Maybe it's synchronous. And as I said, service references themselves are proxies. So one of the goals, I didn't put it in the slide, but one of the goals is that basically everything distills down to function calls. Right? So, worst case scenario, vtables, which is virtual method tables. So code generation is designed to be all single-threaded. Services are single-threaded. They never have multiple threads in them. And single-threaded code is much smaller and much more efficient than multi-thread aware code. Memory barriers are only required now when outside of our own housekeeping statistics and whatnot. Memory barriers are only required when changing the service context, meaning I am no longer working on this service, so I need to make sure I flush whatever that state is, and I'm now working on this service, so I need to make sure that there's a memory barrier that I go through, so if anyone else was working on it, I will see the latest data. Okay. Density. As I mentioned, we wanted to get a lot of stuff onto one server. So hierarchical binary structure. So this is how we actually produce the intermediate representation of the code. And we'll look a little bit at that. How am I doing on time? 15? Don't I get 3 hours? Okay, I'll have to go faster. So file, module, package, class, etc. They just nest like Russian dolls. And So you can have, it's not dissimilar from a lot of IRs. I've built Java assemblers, for example. It's not dissimilar from that, other than it's much more infinitely nested. And things that are logically nested in the language are actually physically nested in the binary. One global constant pool per file, one local pool per method. Now so I wrote an incremental compiler years ago for Java, and one of the pains in Java is that anytime you change something, everything changes, because if you adjust the order of the constant pool, things that were using a 1 byte pointer versus a 2 byte pointer, or so instructions are all byte indexed and they are variable length, and the constant pool indexes are potentially variable length. And so any change, you kind of have to juggle the entire. Is that a teller? Hey, I didn't see it. You have to juggle the entire. You may have to rewrite the entire assembly, the entire class file structure. And so, what we did is we had this deferred optimization where we wouldn't resort the constant pool unless, something big happened. And that allowed us to avoid having to reassemble all the methods. But what we did here is we made one giant constant pool, which is across the entire module or set of modules in a file. And then every method, which has the code inside the method, every method has a pointer table into the constant pool. So it has its own it thinks it's its own local constant pool. And the reason that's really important is that the numbers, and we'll look at this on one of the upcoming slides, all the numbers that we use to identify the constants, by identifying just the ones we use locally, the numbers are all small. And small numbers are actually smaller. And we'll get to that. But the other thing is that now I can rearrange all of the constants in the constant pool, so I could merge multiple files or whatnot, but I don't actually have to disassemble any of the methods, because every method has a list of the constants it uses and an index in that pointer dereference index into the big pool. Did everyone understand that? Anyone? That was the worst explanation I've ever done. So basically, in the constant pool, I have a constant which is number 365, right? And in the local constant pool, I call that 0, right? And I may have one op that points at 0. I may have 100 ops that point at 0. And I really don't care, because if I change 365 to 366, I just change that 0 entry here, because the 0 entry here just says 365. So I rewrite it to 366 and I'm done. I don't care which ops are looking at that number 0. The other thing, this used to drive me crazy in Java. All the Java offsets are byte offsets. With variable length instructions and byte offsets, your world is horrible, because you can't move anything without disassembling the entire code attribute and then reassembling the entire code attribute, which, not that you do that on any given day, but, tool chains do that all the time. So, every time you press a key in IntelliJ, it goes out and searches the entire web. So, just the amount of work that goes on in an IDE is unbelievable. So designing these structures to be friendly for those purposes. Right. So we can defer disassembly. We can do method level assembly, which allows us to do incremental compilation and things like that, and conditionally enables delta compression. So the hierarchy of stuff isn't for what you just built. It's for every version of that module that you've ever built and that you still support. So when you give someone a file, it doesn't just have the current version or the latest build. It has version 1.0 and 1.1 and 1.1.1 and the patch for that and the beta of 2 and so on and so forth. In other words, you can put all those versions in one file. And then we zipper compress as we combine multiple files, we zipper compress that hierarchy. So anything in the hierarchy that's identical is only stored once. So we can store, 100 different versions of an application in maybe 2 or 3 times the size of any one version. And that allows you, for example, to provide patches to a customer that they can optionally use or not use. It allows you to ship your tests as part of your application, because they're conditional, just like a version you can think of as a condition. Well, so is unit testing a condition. And conditions themselves are constants stored in that constant pool. So things like the code can actually refer to a condition. It says this block is only activated if that particular condition, like I'm running in a debugger or I'm currently running a unit test, those are conditions. And by the way, I didn't put any legal stuff on this. This is all open source. Anything you like, just steal. I mean, reuse, recycle. So there's no, I'm not at all. This is not proprietary. So everything's an int. So I said earlier, small numbers are smaller. Having worked on like Java compilers, for example, there's 16. Java is 16-bit in a lot of ways, and most people don't know that because you think, well, it's 32-bit or 64-bit, but yeah, it's 16-bit. You can't handle an exception if your code attribute exceeds 65,530, or is it signed? It might be 32,767. Who knows? For us, everything's a 64-bit int. We just assume 64 bits because it's a big number. No one will ever need more than 640 kilobytes. But actually, our int goes to 512 bytes, so that's okay. So it's so parameters. If I say pass something to foo, the something is identified by an int. It could be register number 1. That's an int. It could be constant number 73, which is encoded as -89 or something like that, -16 offset, and so on. So everything's a number. And when I return a value, I'm returning it into that register, number 4. And or I'm storing it in that property, number -6 or whatever. Indexes. So all of the, I need the third thing from that, or there are 17 things in this list, or whatever. All of those numbers are just encoded as part of a dynamic, as part of a variable length instruction as an integer. So I may encode a call if it has 10 parameters and 3 return values. That's 13 64-bit values, which would be really big, except most of the time that would be a total of 16 bytes. 13, 3, did I get that right? How does this work? Well, most numbers are 0. In a computer, if you do a histogram of all the numbers in the computer, they're mostly 0. And the ones that aren't 0 are mostly 1 or -1. So we're doing well so far. So small magnitude numbers, and then, of course, a long tail distribution out to 2 to the 4095th. That's the 512 byte joke. Okay. I'm here all day. I'm here all week. Packed integers. So what we did is we created, for the 64-bit size integers, we created what's called a packed integer format. So 7 bits. In fact, I can, I think I have this as a, there we go. So this is, this is the prototype, the proof of concept. So this is used by the compiler. So here you can see, up to 7 bits is a single byte. You can see the formats on the right side. So that's called a tiny. For small, which is up to 13 bits and 2 bytes, up to 21 bits and 3 bytes. And then large is up to 512 bytes, which would use 513 bytes total. And so, typical bit whittling stuff. But the nice thing about that is now you don't have to worry that something could be a big number or a small number, and because it's going to automatically compress it down to pretty much the minimum size that you can imagine. So everything's injected. What does this mean? Well, this is I mentioned security is kind of a really big deal early on. So the XVM doesn't actually have any I/O capability. It has no I/O, it has no network, has no storage, has no console, has no log, has nothing. All those things are not in the language. And since they're not in the language, and everything in the language is made out of the turtles in the language, it's impossible for those things to exist in the language. You cannot have I/O, you cannot have network, etc., unless God decides to give it to you. So let's think religiously for a second. When we talk about dependency injection, what we really are talking about is praying, right? So some magic being, you say, dear magic being, please give me a file system. And then you close your eyes, and when you open them, there's a file system in your hands. And you're like, oh, cool. Now I can destroy this computer. Except in Ecstasy, the thing that got put into your hand, it is a file system because it implements that interface. But who knows what it actually is? It could just be a fake file system, mock file system, a file system on an in-memory variable. Who knows? And what it means is if you're running 1,000 different apps and each one's asking for a file system, you're giving them each their own file system, for example. So injection is how did I get back to that slide? That's the wrong slide. Try this one. Everything's injected. So the environment is injected. All I/O is injected. Even the clock is injected. What time is it? There is no system. There is no runtime object. There's no system object. If you need a clock, you say, dear God, please put a clock in my hands. And poof, you have a clock and you can say, what time is it? Right? Why is this really, 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 really handy? Because now you can build a test that actually gets the same exact behavior every time it's run. Right? When it asks what time it is, you can speed up time, you can slow down time. If you're really nasty, you can make time run backwards. Because that's what network protocols do, right? Okay, so even the clock is injected. Designed for unit testing, easy mockability. In fact, we have a keyword called delegates, so you can, and we have a keyword called to do, so you can delegate an entire type to the to do expression, which means you just mocked an entire 100 method interface in one line of code. Of course, to do throws an exception, but isn't that what you do most of the time in the mock anyway? Injected references are masked. So what this means is if God has a super duper file system that can do anything on the computer, like root and blah, 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 and he wants to inject this implementation into my container, what comes in is not the super duper file system. It's actually a proxy for the super duper file system that's limited to the interface that's declared on the injection. In other words, what I get is just a file system. And I'm like, oh, what class are you? It's like, I'm not a class, I'm just a file system, right? So it's impossible to unmask that reference. And so injection becomes so we strip all undeclared surface area from the injection site. So I try to illustrate this with the child's toy where you have to put different shapes in different holes. But the contract is type and name. So you say inject, a random object, let's call it secure. So I want some secure random. So it's type and name. I can use this for environment, for configuration, for services like I/O services, or I inject my own types, right? Because it's all hierarchical, so I can nest a world under it. So if you think of those types, this container gets the great. I obviously don't know how to use this thing. Going back through this container needs these. That's its contract. It says you can't load this type system unless you agree to inject these three things. If you can't inject those three interfaces, you can't load this container. So that's the container contract. And then internally, it creates another container, and it allows, for example, that injected thing that it got to go straight in there. But it also, that container needs something that isn't in this contract, so we have to make it here and inject it into that container. So in other words, injection is also hierarchically nested. Here's an example of what source code looks like. That's the hello world example. Console is I/O, so like I said, you can't have something that does I/O in the language, so it has to come from God. And now let's talk about instructions. So I'm going to run through this because we're down to like 4 minutes. So the big point I want to make here is that our assembly reflects the AST almost 1-to-1. You like that? So we don't do a lot of what we call syntactic sugar. Like if it's syntax, it pretty much becomes assembly. Not because we want the assembly to look like the syntax, but because the information in the source, we can't enrich in it, if you will. We can't enrich that data in a compiler. So any change that we make will just lose information. Think about it that way. So we carry the maximum amount of information. So these are actual instructions. This one says, hey, this method starts at line 13 in the file. This is a guarded block. There's a guard end. There's a catch. There's a catch end. There's a return. These are method invokes. Takes 0 parameters, 0 returns, and so on. By the way, this is a register machine, not a stack machine. We do have a stack, but it's only a shortcut for creating temporary registers. So it's not really a stack. It's a fake stack. It's a register stack. So methods can take any number of parameters and have any number of return values. I don't know who's responsible for deciding that methods and functions should only return one value, but I think that's horrible and evil. Once you have the ability to work with more than one return value, you will never go back to a language that does not support it. So instructions like call, which is a function call. So we have functions, which are objects. Everything, by the way, is an object. Invoke, which is a method invocation. It's like a call, except it requires a target binding first. Return, obviously at the end of a function or method. New, the C versions of new are the plus C suffix on that is a child, so virtual child. Very complicated, so I'm not going to explain that. But G is a generic type because it has to go through resolution. And then constructor calls. So all of these are kind of your basic building blocks, and then they have suffixes of 0, 1, N, and T. As you saw on the previous slide, invoke 0, 0 is invoke passing 0 parameters, returning 0 return values. So we can pass none or 1. These are just compressed ops. These are all variable length ops, but obviously it's small when it's a 0. N says I'll tell you how many there are, and then I'll follow that with that many values. So if it's 5, I'll have the number 5 followed by 5 numbers. That's why index compression is so important. Index being number, integer compression is so important because we use them everywhere. And then tuples. So you can treat parameters as tuples. You can treat return values as tuples. So there's obviously a lot of combinations there between those instructions. We have logical and branch instructions like jump and is. This is logical with a jump. So like jump 0 says that's a numeric type. If it's 0, jump to whatever that address is, and so on. Scopes and expressions. So enter exit defines a scope. So think of that as your curly braces. There are other instructions that implicitly define a scope as well, like guard end would be a scope in and of itself. And the types of all the registers are known, so it's strictly typed. It's perfectly typed, meaning there's no slop, which means, well, we can go into what that means in the covariance system, but it basically means you may have many different references to the same object because some of those references have to guard against certain type mismatches. While others of them will only be used in situations where the types are perfectly known, so it doesn't have to do those checks. So basically, we can skip all the preambles on all the methods if we know what the types are. And in cases where we can't guarantee to know the types at compile time, we can produce preambles that do that runtime check. So these are various catch and throw stuff. Variable declaration. So like var in would be, that's the most common one I think that we use. It's an initialized variable named. So if I say int I equals 0, that would be a var in followed by 2 constants, one that points to the string I and one that points to the number 0. Let's see, binding. We can take a method and bind it to a target, and that gives us a function back. We can take a function and bind some of its parameters or all of its parameters and get a function back as a result. So whether you want to call it currying or binding or partial binding, it does all that. And we also support on the language side, call by index, call by name. So I can I can pass parameters by name. I can pass them by position. I can pass them by binding, etc. So, every language has to have a move. Every instruction set has to have a move. This is a type assertion. As you can tell, when we designed it, we were still thinking in terms of casting. We don't have casting with type assertions. And then we have actual assert ops, like this one, for example, is used when the compiler determines that an assert expression has information that the developer wants to see. So if you say assert x is less than 0 or x is greater than 255 or whatever, it'll actually print out, oh, x wasn't greater than 2. It'll tell you which part of the expression it failed, and it'll tell you what the value of x was. And that's this instruction. And it does that with no additional runtime cost other than one register. Okay. Kurt. Downcasting. Example.
Well, you said something, so I think super subclass type relationships in language, since we haven't seen that.
Yes. So there is an object class, for example.
So if you think of some of the pattern encoding patterns you use, then you would pass, maybe it's passes one to the super class.
Mm-hmm.
But when you call against it, you actually want it to go against the real type of the super class.
Correct.
Which is broken in Java.
Oh, well, it's virtual calls in Java, right?
Yeah, well, okay. Never mind.
But yes, the same. It'll feel the same way in terms of being able to pass something as a super type. So I can pass a string as an object. I can pass an int as an object. And then I can, if I have to treat that object as an int, I have to type assert that it is an int. So the keyword as is used for type assertion. So you would say, you have an object O, you'd say O.as int dot whatever you want to do with it.
Oh, unfortunately.
Other questions? Wow, I didn't answer everything, so there must be some question. Come on, Attila, give me a tough one.
All right.
Never one to disappoint.
So you said that the model is running on terabytes of RAM and thousands of cores. Are you also supporting a model where you actually distribute the system across multiple machines?
So no, we do not have that in the plan. So having worked on distributed systems before, that's not something that I personally felt was in the realm of the runtime itself. So, however, as you can tell from some of the design decisions, they are strongly influenced by things learned in distributed systems, like the value of immutable objects, for example.
Right.
Hi, David.
Hi.
These things given by this deity, how do you implement those?
So those can be implemented in Ecstasy. The only things that can be injected that are native have to be injected into the 0 container, because there cannot be native code inside Ecstasy. So that means if it's not injected from the outside into the initial container, it cannot be injected. And again, that's part of the security model. It's neither accidental nor bad. How's that?
That's good.
I saw a question on this side. Yes.
Do you have a couple of more information about the actual virtual machine at the end of the day? I just went to GitHub and saw that you wrote most in Java.
Yes. So the proof of concept is built in Java. So the existing implementation is just a proof of concept. It's words I would not use to describe it include efficient. But that's not its job. Its job is simply to prove out that. So the reason once we get the verifier done, then we'll probably port it into Ecstasy itself. It's a long story, but we're trying to avoid having to write it 3 times. So twice would be enough. So we plan to bootstrap it in Ecstasy, which means we'll need the current POC, the current proof of concept, to actually run what will be the native compiler, which will be written in Ecstasy itself. So it's a bootstrapping exercise. Other questions? Going once?
So
You mentioned that there's one thread per container, but that containers can nest. Do each of the nested containers get their own thread, or do they share that with parents?
So it's not that a container gets a thread. It's that a service has at most one thread. So every service either has 0 threads executing in it or 1 thread executing in it. And a container is a service. So a container could conceptually have 10,000 threads executing inside the container at any given time, or it could have 0. And one of the reasons for making it hierarchical, by the way, is so that we can get rid of a container, just pop it, it's gone. So that, once that entire hierarchy is decided, for whatever reason, whether it's running or not, you can just, it's encapsulated by its design, so it's gone. So did that answer the question? Okay. Kurt?
So
I just have one more question, and it's I'm not sure if it was clarified at the beginning, but why? What is going to be the motivation for people? Why you think people should move to this system as opposed to continuing on out of Java or something like that?
Yeah, I mean, I still personally love Java, but there are things that we've learned over the past 25 plus years that that a new generation of developers deserves to get to experience. Some of those things may show up in Java, but the cost of incremental change in Java is close to infinite, and cost of incremental change in a greenfield project is close to 0. There are certainly advantages to having an existing, stable, beautiful ecosystem like a language like Java has, and there are certainly advantages to being able to create an entire new instruction set and VM and language from scratch.
So was there supposed to be a cloud play in all of this?
I was trying to avoid talking business. So the reason that this language exists is because the company that we started, our product is actually going to be a hosting platform for these applications built in this language. And about 99% of the apps that we host will host for free. And the reason we can do that is because they won't cost us anything to host anything. They'll cost us hopefully pennies a month to host most applications, because most of the time applications are doing what? Nothing. Most of the time when your application is doing nothing, what are you doing? You're paying for it. So this is a serverless model, but serverless, not Lambda, is like serverless bastardized. This is actual serverless. This is designed for real serverless managed workloads. Did that answer?
yeah,
Closer? Yes.
The target furthest down is very, very tired. I want to swap it out.
So I didn't catch that.
The turtle furthest down is very tired. I want to change it. Runtime.
The turtle for
Furthest down.
furthest down.
Yeah.
I see.
I want to change my type system. I want to change one of the lower level containers.
Yes.
Runtime.
So the type system itself is immutable. So this actually plays to Attila's question. So how would you deal with, for example, upgrading the system at runtime? And the way that you would do that is by bringing up a different version of the system. So I'm not talking about a change to an application. It could easily be done by just creating another container. So I could, from one file that has 10 versions of the application, I can load all 10 versions in 10 different containers, no problem. But if I want to change, the version of Ecstasy that's running, then I would have to start a new process.
Or your stuff doesn't container further down, because if you have a hierarchical model, you might want to change one of the middle tier turtles, because one of them isn't doing what it's supposed to be doing.
Right, and exactly. So the idea is that spinning up a container. So I didn't get into this, but the idea is that The verification process and the linking process is generally done once. So basically, you have a persistent statistics image, a persistent linked image, so an SO or a DLL. So you take all the modules, you do transitive closure over the modules, you collect the entire type system, you're compiling it against a given version of the runtime itself. So you do all that compilation up front. It has built into it the statistics gathering capability and the ability to reload portions of it for adaptive compilation. And then that's set on the disk. So when you load an application, you're just loading a DLL, basically, loading a dynamic library. And so getting into, we're over time. So anyway, the idea is, to be able to load an application in milliseconds. So, all right, well, thank you. Great questions, and have a great conference.